symplectic structures on each fiber, and therefore, to make this existent, we took here only the Schwarz section. But eventually we complete that. Here again, the group structure of sections. You have the sections, then lambda times E, lambda 1 times E here, another one here. And here you multiply out, except that you pay some attention to this part. That's a central extension, of course, of the Hillian group. This is also a semi-direct product in finite dimensions, but I don't want to go into that. The Heisenberg algebra works in the same way. Again, this very big center here. See, the brackets are just made up by the symplectic structure, which eventually the canonical commutation relations stem off that symplectic structure. That's where these canonical commutation relations are hidden. The sections, the smooth sections, are in fact Schwarz sections. They are modules, and these modules determine the vector field up to equivalence. What do I mean by equivalence? Two vector fields are equivalent if the line bundles are isomorphic. You have a bundle isomorphism here which subduces to a diffeomorphism, and that's how it works. Now it passes to the group algebra. You see, we have this whole construction is made on purpose. Given the vector field, at least one representation. Not a bunch of representations, say, there is a bunch of representations, but we have not a field of representations or some such, but one representation. Since it isn't unique, of course, we have a lot of representations. And then we want to establish the canonical commutation relations. So we need an object which we really can represent. Of course, we could get a bunch of representations from the Heisenberg algebra, but then for every point we have a known quantization. But that would not that indeed yields a quantum mechanics at that point, but it does not give a total representation of the field. So we want to make a total representation of the fields. Therefore, we form here the group algebra. The group algebra is formed as follows. You take the Heisenberg group bundle, this infinite dimensional one, and you take the C-valued functions with finite support. So that's what you do in linear algebra, in first course linear algebra. Then you have a convolution here, defined in this way. S is, of course, a section or an element of this big Heisenberg algebra. And that's how the convolution is defined, of course. One sums over S, and the sum exists because of that finite support. We have an involution, which is given by inverting the section here. That means, in the group sense, that means in fact minus S on the S level, not on the delta level. And the Heisenberg group can be embedded into the group of in this group algebra. Each S has its own delta function. That's a homomorphism, that's injection. So that's an enlargement, a huge enlargement of the already infinite dimensional.
Is that delta function in any way related to what I was talking about, my capital delta?
At one point you said we could pass to the, or one can pass to C-star algebras. And those are the elements of the C-star algebras. I do not take your general way, I have left it already by looking at the Heisenberg groups, at the Heisenberg group bundle. I now enter the C-star algebras, and now everything goes as you would have C-star algebra. So out of a vector field, I will construct a C-star algebra. That's C-star algebra is a completion of this star algebra. It's a star algebra. We see it here. You have an involution, and it's an enlargement of the Heisenberg group. Now comes a crucial point. We talked about the Weil algebra too, and here it's an explicit sort of Weil algebra, simply because we have constructed it out of the vector field. In physics, you usually take any sort of star algebra and then define a sort of a field quantization. But here, I take the associate a quantization to that particular vector field. But of course, we know that there are many representations due to the lack of the Stone-Neumann theorem, which dictates the local, the pointal quantum mechanics. Now here, we begin to disturb the star product by taking the symplectic structure caused by the vector field. This is a sort of a bi-character, there are two characters here, and this is skew. And you see here that the new product is certainly non-commutative. It's a phase factor which does not, where non-commutativity is implemented. The canonical commutation.
Is that really delta S1 star delta S2 there?
Yeah, that's
not the other way around?
No, 1, 2.
1, 2.
But of course, the other way around.
Oh, it's because of the way you defined your omega.
Yeah, yeah.
Okay.
That is not. Now, each section in here of the Heisenberg group bundle causes a linear function. Namely, you see the linear functions of that algebra here are a basis of the linear functions are the dual variables of the delta function. And that's precisely what this means. And this linear dual space inherits a new product, Weil's product. Namely, you had it too. Namely,
yeah, but I put it in. I brought it out of the air and
yeah,
put it in.
Here in the example, such as to say for your theory, of course it is structurally determined, but it's due to the example. In the fact it's an example. You take the Weil element of these two delta, of the sum of the delta function, of the sections, of course, again a delta function. You perturb it by this phase factor, and that's then a new product. And of course, this thing here eventually will give me the Weil algebra. And the canonical commutation relations are hidden in this Weil product, namely in integral form.